Enolates, as we introduced last time, are going to be crucial to understand the mechanisms in this chapter. They turn the alpha carbon into a nucleophile. And so this video is meant to help you to visualize, to see those enolates even before they're formed, to sort of train your mind when you see a ketone to see the enolate and to see how it can react. And we'll use that ability in larger mechanisms in future videos. So in these cases, they want you to draw the two resonance structures of the enolate formed when each of the following ketones is treated with a strong base. It's a similar scenario as in the previous video. In each case, you'll have alpha hydrogens. Remember, you have the carbonyl carbon. Next door to it, those carbons are the alpha carbons. So in this chapter, we're learning about the reactivity of those alpha carbons. So when you look at a molecule, the alpha carbons should be very special to you. There should be something that stands out. Now, it's not the alpha carbons themselves that are reactive. It's the fact that the hydrogens on them are acidic. The hydrogens on them can be ripped off because the electrons that were in the bonds, if they're a lone pair, can be stabilized through resonance. Now, we're going to draw all the different resonance structures here, so we'll unpack that. But we also talked about that a lot in the previous video. In this first structure, it's symmetrical, so I'm just going to look at the right side. Both would be the same. In the second structure, an important thing to notice is that there is no hydrogen on this alpha carbon on the right. Our 4 bonds are already drawn in, and so that alpha carbon will not end up being reactive. But the alpha carbon on the left does have a hydrogen. It has more than one. I'm just going to draw one, and you'll see how that gains reactivity from that hydrogen being there. Same thing with C. This alpha carbon on the right does not have any hydrogens, so it's not going to have the special reactivity. But the one on the left does, and so it will. Same thing in D. The alpha carbon on the left has 4 bonds already, so there's no hydrogen there, and it won't just act as a nucleophile. But the alpha carbon on the right does have a hydrogen, and so that will act as a nucleophile, as you'll see. For E, notice there is only one alpha carbon. This is an aldehyde, so this is a hydrogen on the left, not a carbon. And there is a hydrogen attached to that one alpha carbon. So that will have that special reactivity. So we've taken a second to notice all the alpha carbons and draw in any hydrogens that are on the alpha position, because those are what are vulnerable to a strong base. So if we add hydroxide, it doesn't have to be hydroxide, it could be any strong base. But if we add hydroxide to each of these, let's see what happens. So in each of these cases, the hydroxide steals the alpha hydrogen, and the electrons snap back onto the carbon that the hydrogen was bonded to, the alpha carbon. And the reason why it can do that is because when you redraw the structure you get, you have a lone pair there, and that lone pair is allylic. Well, a lone pair with a negative charge. That lone pair is allylic. It is one atom away from an atom in a double bond. And so you have p orbitals, parallel p orbitals on these two atoms that are creating the pi bond. This exists in another p orbital. These are all parallel, and so the lone pair can spread out through all of them through one sort of continuous pi bond. So you get a resonance structure. That's one of the 5 resonance patterns, and it's going to be stabilized through resonance. We'll draw all the resonance patterns together, but first I just want to emphasize and sort of ingrain in your mind that the strong base steals the alpha hydrogen. The electrons snap back onto the alpha carbon, and they give you a resonance stabilized lone pair. So again, the base steals the alpha hydrogen, that's the vulnerable hydrogen. The electrons snap back onto the alpha carbon, and they're able to do that because it produces a resonance stabilized lone pair. on that alpha carbon. So the base steals the alpha hydrogen, the electrons snap back onto that alpha carbon, and that hydrogen is able to be ripped off because the conjugate base it leaves behind is stabilized through resonance with the carbonyl. As we shall see in a second. And again for E. Now, don't be tempted. This is not an acidic hydrogen. That is not on an alpha carbon. It's on the carbonyl carbon. The acidic hydrogen is on the alpha carbon. That's the one that the base steals. These electrons snap back onto the alpha carbon. And so you have that lone pair there, that allylic lone pair that's going to be stabilized through resonance. Okay, so far we have trained our eyes to see the alpha carbon and specifically the alpha hydrogens on it. And that is an important feature of an aldehyde or a ketone because that alpha hydrogen is acidic. You can treat it with a strong base and you get this allylic lone pair in each of these cases. To draw the other resonance structure for an allylic lone pair, you draw the lone pair going toward the pi bond and the pi bond going away from the lone pair. So you draw your resonance arrow, and this lone pair becomes a double bond, and the pi bond turns into a third lone pair, which now has a negative charge. So you can see that this is an enolate, So that's the resonance-stabilized enolate, the two resonance structures of the enolate that are formed when you treat this ketone, these ketones or aldehydes with these strong base. So again, you have that allylic lone pair. To draw the other structure, the enolate, you draw the lone pair forming a pi bond toward the pi bond, and the pi bond forming a lone pair away from the incoming lone pair. And so you have your enolate. In this case, you have that lone pair going toward the pi bond and the pi bond going away from the lone pair. And so you have your enolate. In this case, you have the allylic lone pair, so the lone pair goes toward the pi bond goes away from the lone pair. And so you have your enolate. In this case, the lone pair goes toward the pi bond goes away from the lone pair. And so you have your enolate. And notice this happens with an aldehyde just as well as with a ketone. So the point behind all of this, the meaning behind all of these details, is that the alpha carbon is acidic. If you treat it with a base, that alpha carbon becomes a nucleophile. And it becomes a nucleophile because the hydrogen is acidic and can leave and can turn the alpha carbon into a nucleophile because the lone pair there is stabilized through resonance. So remember, resonance tells you how much charge spreads out. That dilutes charge and stabilizes molecules. The more resonance structures a molecule has, the more stable any charge is in that structure. So when you see ketones or aldehydes now, you should see more than one molecule. You should see the ketone or the aldehyde, but you should also, with your chemistry vision, see the enol or the enolate. You should, in terms of reactivity, you should see the carbonyl carbon as a great electrophile, as we've seen in previous chapters, but you should also now see these alpha carbons as potential nucleophiles. And that's going to be really important in explaining the reactions for the rest of this chapter.